My name is Agatha Ulibarri, and I worked on optimizing small angle polarization rotations this summer. Why do we want to measure small angle polarization rotations? Well, we can use it to determine optical magnetization in semiconductors. Photons incident upon a semiconductor carry angular momentum, which is conserved in the charge carriers, causing a magnetization of the material proportional to the polarization rotation of light. We can also use rotations to determine the thickness of chiral thin films, because the rotation angle is proportional to the thickness. I was tasked with comparing the effectiveness of two different optical bridge setups: the polarizing beam splitter, which splits the S&P polarized light at a 90-degree angle with an extinction ratio of 1,000 to 1, and the Wollaston beam splitter, which splits S&P light at a 10-degree angle with an extinction ratio of 100,000 to 1. PBS is easier to align, while the Wollaston has a higher extinction ratio. The Wollaston was found to give polarization rotation angle measurements 2 times smaller than the PBS, so now to compare this to a third measurement called the phase-generated carrier technique. The PGC technique uses a photoelastic modulator that modulates the rotations at high frequency. This is ideal because it measures outside mechanical vibration frequencies. However, using just the Wollaston allows us to increase the gain for a larger signal. The optical setup for the PBS bridge is as follows. A sample of magneto-optical material is placed in a solenoid, which can cause a known rotation of polarization. This is so the results can be sanity checked after the measurement. The difference of the intensity on the two detectors can be determined using Jones matrices, and it can be found that the rotation angle is proportional to the difference of intensity on the bridge over the initial intensity. The Wollaston beam splitter is similarly set up. However, the detectors must be placed at 10-degree angles to the optical axis. This has proved difficult to align. The phase-generated carrier technique setup now uses a PEM sandwiched between two oppositely oriented quarter wave plates, with the Wollaston bridge still intact. Two lock-in amplifiers are used to determine the intensities of the first and second harmonics given by the PEM. Because of the Jones matrices, we know that by taking the ratio of these intensities, we can determine the rotation angle. The results of this last comparison have so far been inconclusive. However, further experimentation is expected to elucidate the answer. Thanks to all the people and institutions that have made this opportunity possible.